other way to solve for the percent voltage regulation, our second step or second method is the Rothert's MMF or Ampere turn method. So our first method was the synchronous impedance method or the EMF method. So in MMF or Ampere turn method, it also utilizes OC and SC, the open circuit and the short circuit data, but is the converse of the EMF method in the sense that the armature leakage reactance is treated as an additional armature reaction. So in other words, it is assumed that the change in terminal potential drop on load is due entirely to armature reaction and due to the ohmic resistance drop, which is in most cases is negligible. So otherwise, it is stated or it is given the armature reaction or the ohmic resistance drop. This fact is shown in figure 37.43. This one. So in Ampere turn method, this one is most cases is negligible. But it depends on the problem if RA is given. So you need to solve EO with RA if RA is given. So if RA is not given, nandito lang yung XA. So XA will be just used. This one. The drop in XA is used to solve for the EO as well as your terminal voltage. Now, field ampere turn. The field ampere turn required to produce a voltage of V or the terminal voltage on full load is the vector sum of the following. So first is the field ampere turn required to produce the V, or if RA is to be taken into account, if your RA is given, so it is the sum of V plus the drop in your RA on no load. So this can be found from our curve OCC curve. And the field ampere turn required to overcome the demagnetizing effect of armature reaction on full load. This value is found from short circuit test. The field ampere turn required to produce full load current on short circuit balances the armature reaction and the impedance drop. The impedance drop can be neglected because RA is usually very small and XS is also small under short circuit conditions. Therefore, the power factor on short circuit is almost zero lagging, and the field ampere turn are used entirely to overcome the armature reaction, which is wholly demagnetizing. So in other words, the demagnetizing armature ampere turn on full load are equal and opposite to the field ampere turn required to produce full load current on short circuit. Now, if the alternator, instead of being on short circuit, is supplying full load current at its normal voltage or zero power factor lagging, then total field ampere turn required are the vector sum of, first is the field ampere turn in figure 37.44 OA, necessary to produce normal voltage as obtained from the OCC, and the field ampere turn necessary to neutralize the armature reaction, which is the vector AB1. The total field ampere turn are represented by OB1. So that is in figure 37.44. In figure A, equals to the vector sum of OA and AB1. The vector OB1, this one, the vector OB1 is the sum of OA and OB1. OA and AB1 equal to OB1. In figure B, If the power factor is 0 leading, the armature reaction is wholly magnetizing. Hence, in that case, the field ampere turn required is OB2, which is less than OA by the field ampere turn that is equal to AB2 required to produce full load current on short circuit. That is in figure 37.44b. If the power factor is unity, the armature reaction is cross-magnetizing. Its effect is distortional only. Hence, field ampere turn required is OB3 such that the vector sum of OA and AB3, which is drawn at right angles to OA as in figure 37.44 letter C. So for general case, this one is for the lagging power factor, leading, and unity power factor. Let us consider the general case when power factor has any value between 0, lagging or leading, and unity. Field ampere turns OA corresponds to V, or if RA is given, you can solve V plus IRA drop is laid off horizontally. Then AB1 representing full load short circuit field ampere turn is drawn at an angle of, for lagging power factor, it is 90 plus your angle theta, your power factor. This one. This is your power factor and 90 degrees for lagging. For leading naman, ito yung theta. And this is your 90 degrees. For unity, so nandito lang yung 90. The total field ampere turn are given by OB1 as in figure 37.45a. For a leading power factor, short circuit ampere turn is equal to AB2 is drawn at an angle of 90 minus angle theta. And for unity power factor, AB3, that is letter C in figure 37.45. So in those cases where the number of turns on the field coil is not known, it is usual to work in terms of field current as shown in figure 37.46. In figure 37.47, the complete diagram along with open circuit and short circuit characteristics. OA represents the field current for normal voltage V. OC represents the field current required to produce or for producing full load current on short circuit. Vector AB is equal to OC is drawn at an angle of 90 plus theta to OA. If the power factor is lagging, the total field current is OB, for which the corresponding open circuit voltage EO. Therefore, the percent regulation will be equal to EO minus V divided by the V times 100. So it should be noted that this method gives results which are less than the actual results. That is why it is sometimes referred to as optimistic method. So in the previous method, which is the synchronous impedance, it has a larger results than the actual. So mas closer yung Rotherts into actual or inactual compared to the synchronous impedance method. Let's have an example. 3.5 MVA Y connected alternator rated at 4,160 volts at 50 Hz has the open circuit characteristic given by the following data. So we have field currents 50, 100, 150, 200, 250, 300, 350, 400, and 450. We have the voltages, EMF volts, in three-phase from 1,620 to 5,750. Field current 50 has a voltage of 1,620 and so on and so forth. So a field current of 200 amperes is found necessary to circulate full load current on short circuit of the alternator. Calculate by synchronous impedance method and ampere turn method the full load voltage regulation of or at 0.8 power factor lagging. So neglect resistance. Here we neglected the RA. Only the XS will be used. So we have apparent power equal to 3.5 MVA. Our output voltage is 4,160 volts. We have a power factor of 0.8 lagging. Here our field current is 200 amperes on short circuit. So in our synchronous impedance, the formula for Zs is equal to the open circuit voltage divided by the short circuit current. For the open circuit voltage, we have at 200 amperes, field current 200, its open circuit voltage is 4,750 in three-phase. So we need to convert this one into per phase. So we will divide this one by square root of 3. 4,750 divided by square root of 3. Also, for the short circuit current, we have the full load current is equal to 3.5 times 10 raised to 6 divided by square root of 3 times the output voltage equal to 4,160 volts. That is 485.751 amperes. Our armature resistance is equal to 0. So synchronous impedance now will be 4,750 divided by square root of 3 all over our short circuit current, 485.751. That is, since RA is 0, the remaining component will just be the inductive. So that is J 5.6 ohms per phase. We will draw the vector diagram of this one. This is our terminal voltage, and this will be the graph of your IXS because RA here is neglected. Before, this one is like this one. Ito yung V natin, yung drop ng IRA and IXS. But IRA is equal to 0, so ito na lang yung natira, IXS. The sum of terminal voltage plus IXS will be your no-load voltage. And no-load voltage is equal to 4,160 divided by square root of 3 times or plus 485.751. The power factor angle is negative 36.87 multiplied by Zs. So our Zs now will be equal to I or XS because RA is 0. So J 5.65. Or you can solve this one EO using cosine law. Cosine law, ito ay 90. And this is your angle theta. Okay? The same lang yung makukuha nyo. So, EO is equal to 4,605.512 angle 28.47 degrees volts. Computing now the voltage regulation under synchronous impedance method. That is 4,605.512. This is plus or minus. So, this is minus 4,160 divided by square root of 3. Divided by 4,160 divided by square root of 3 times 100. Percent VR now will be 91.75%. For the second method, we have the Ampere turn method, the full load voltage regulation at 0.8 power factor. So, here I already graphed the given parameters, which are in y-axis, we have the voltages, open circuit voltages, and on x-axis is the field currents. So, for 50 ampere, we have 1,620. 100, we have 3,150, and so on and so forth. So, if we graph this one, the points, our OCC will be look like this one. So, this is our OCC. For your activities, you will use graphing paper para i-graph nyo yung mga field currents and voltages. Now, after nyo matrace tong mga points na to, we will have your 150, which is the voltage, the normal voltage, 4,160. Its corresponding field current is 150. This is our 150. And the IF, field current, equal to 200 amperes, the current on short circuit. Our field current here, which is 200 amperes, ilalagay natin dito, which is corresponds to ISC. And then, we will now get your, let's say, total current. You can solve this total current by cosine law. So, eto na yung 90 plus theta na sinasabi kanina. So, IT now will be equal to 150 square root of 150 squared plus 200 squared minus 2AB, which is 2 times 150 times 200 cosine of 90 plus 36.87 equal to 313.8 amperes. Now, this 318, we will reflect this one in our OCC. This is our 313. We will reflect in our OCC curve, and then we will get now the EO, or the no load voltage. So, at 313.8 amperes, it has 5,440 volts, no load. Therefore, our percent voltage regulation will be 5,440 minus our terminal voltage, which is 4,160 divided by 4,160 times 100, equal to 30.7%. So, as you can see, the calculated percent VR in synchronous and in ampere turn are very large in gap. or I mean malayo yung agwat nila. In reality, the actual percent voltage regulation of an alternator has close value to the Rothert's method or the Ampere turn method. So simple lang, simple lang yung pagkuha ng Rothert's or I mean paggamit ng Rothert's. Kailangan mong ma-solve muna yung IT and then i-reflect mo dun sa graph. And then you will now get the no load voltage and then you can solve for percent VR. Second example, we have the following test results are obtained on a 6600 volts alternator. For the open circuit voltages, we have 3100, 4900, and so on and so forth until 8300. Field current 16, 25, 37.5, 50, and 70. A field current of 20 amperes is found necessary to circulate full load current on short circuit of the armature. Calculate by Ampere turn method. So we will just use the Ampere turn. Full load regulation at 0.8 power factor lagging. We will solve the voltage regulation at 0.8 power factor lagging using Ampere turn method. So here, I plotted the open circuit voltages and the field currents. So this is the result of the OCC. So for our voltage, terminal voltage, that is 6,600 and 6,600 has a field current of 37.5 amperes. So what will be the value of your EO? Our field current at ISC is 20 amperes. So this is our 37.5 and this will be our 20 amperes. Getting the value of IT, that is the cosine law, we'll use cosine law. IT is equal to the square root of 37.5 squared plus 20 squared minus 2 times 37.5 times 20 cosine of, since this is a lagging power factor, 90 plus 36.87. Our IT will be 52.02 amperes. Now reflecting this 52.02 in our OCC curve, we will get an open circuit voltage which is equivalent to 7,600 volts. So EO, no load voltage, will be 7,600 reflected in our OCC. So percent voltage regulation now will be 7,600 minus 6,600 divided by 6,600 times 100. So that is 15.16%. Our last example will be the open and short circuit test readings for a three-phase star connected 1000 kVA 2000 volts 50 Hz synchronous generator are. Our field currents are 10, 20, 25, 30, 40, and 50. The open circuit terminal voltages 800, 1500, 1760, 2000, 2350, and 2600. Short circuit armature current in amperes. So in field current, we have 200 amperes. In field current of 20 amperes, the short circuit armature current will be 200. At 25 is 250 and at 30 is 300 amperes. The armature effective resistance is 0.2 ohm per phase. Draw the characteristic curves and estimate the full load percentage regulation at 0.8 power factor lagging and 0.8 power factor leading. So in our problem, our RA is given, which is 0.2. So our the apparent power of this alternator is 1000 kVA. Its terminal voltage is 2000 volts, frequency is 50 Hz. Calculate the voltage regulation at 0.8 lagging and 0.8 leading. Now, since this is a three-phase star connected, we will convert all the open circuit terminal voltages into per phase because in a Y-connected load or Y-connected alternator, the line current and the phase current are equal, but they are differ in terminal voltages, which is, remember in your circuits that E line is equal to the square root of E phase. The given OC terminals here are in three phase. So our single phase open circuit terminal voltages now will be 461.88, 866.03, 1016.14, 1154.7, 1356.8, and 1501.11. So I already plotted all the parameters. In y-axis, we have the open circuit voltage per phase. So nandito yung mga per phase natin. In x-axis, we have the field currents. This one, IF. And the other side of y-axis will be your short circuit currents. If you will graph all the single phase OCTV and versus the IF, it will look like this curve. This is our OCC. And short circuit current corresponds to IF. This will be your curve or graph. This is SCC. Now, we are going to solve for the full load current of the alternator. So, IFL is equal to apparent power divided by square root of 3 times our voltage. So, 1000 kVA divided by square root of 3 times 2000. Since 2000 is our terminal voltage, IFL will be 288.675 amperes. So, we will reflect this to SCC and get the field current to produce this current. So, IFL 288.678. So, nandito siya. And we will reflect it to our SCC and we will get its field current. So, that is equal to 29 amperes. For our full load voltage naman, it is equal to terminal voltage plus IFL multiplied by RA since RA is given. Then reflect to OCC, then get the field current necessary to produce this voltage. For lagging power factor, we have EFL is equal to 2000 divided by square root of 3 plus our field current or full load current 288.675 angle negative 36.87 multiplied by our RA 0.2, that is equal to 1201.39 angle, so angle something, hindi ko na nasulat. So reflect EFL at OC curve, then get the full load or field current. So if we reflect this one, EFL, the 1201, what will be our field current? So, nandito estimated yung 1,201. You will get 32 amperes to be its field current necessary to produce this voltage. And then, IFL at SCC, our 288 a while ago, reflect it to SCC, we will get 29 amperes. This one. This will be our field currents, 32 for our OCC curve and 29 for our SCC curve. Then we will get I using cosine law. So IT or I is equal to the square root of 32 squared plus 29 squared minus 2 times 32 times 29 cosine of 90 plus our power factor. That is 36.87. IT now will be 54.577 amperes. So this triangle, we will reflect it to our graph like we did in our previous examples. So if we will reflect this triangle here, its corresponding value of I is OC corresponds to a field current of 54.577, that is equal to 1,555 volts. So if we will put this triangle here and you will have 54.5771 approximately here, 54, and then we will reflect it to the OCC curve. So you can extend this one. You can extend our OCC. And if you will reflect the 54 something in our OCC, you will get 1,000, approximately 1,555 volts. Then you are now ready to solve for the percent voltage regulation. So that is EO minus V divided by V. This 1555 is our EO. So 1,555 minus 1,155. This 1,155 is 2,000 divided by square root of 3. All over 1,000. This is 1,155. Percent voltage regulation now in lagging power factor is 34.6%. For leading power factor, same, we have a field current of 32 amperes from our OCC and we have our 29 amperes from our SCC. But the only difference is the orientation of your vector. This is a leading power factor, so this is our power factor 36.87, and IT now will be equal to square root of 32 squared plus 29 squared minus 2 times 32 times 29 cosine of what will be this angle. So that is 90 minus our power factor, which is 36.87, equal to 27.41 amperes. Then we will reflect this again, this triangle, we will reflect this in our graph. And then after putting your triangle here, you will reflect it again to your OCC curve. The corresponding OCC or the corresponding no load voltage for this 27.41 ampere is 1,080 volts. So percent voltage regulation is equal to 1,080 minus our terminal voltage, which is 1,155 divided by 1,155 times 100. So in leading power factor, we have a percent voltage regulation equal to negative 6.4%.